So welcome back to everyone. This has been a great morning. I hope that you're enjoying being here with us. And we are pleased to present our next panel, which is data from the satellite to the scientist's computer. So Amy will be monitoring the Q&A sort of in the background. And then again, these sessions are more fun with audience participation. So please do submit your questions in the Q&A over in Whova. And then feel free to chat with other attendees over there in the chat. So I have the pleasure of introducing our moderator, Professor Alvar Sanz Otero. Alvar is our newest addition to the faculty in aeronautics and astronautics here at UW. He teaches capstone courses and systems engineering. He completed all of his professional degrees at MIT. His doctoral research concentrated on the development of space-based microgravity laboratories for operation aboard the International Space Station. He applied his knowledge in electrical engineering and computer science to the development of the SPHERES laboratory. I don't know if you're going to show that at all, but it's super cool. You can look it up on the internet. We can put a link in. As a principal research scientist at the MIT Space Systems Laboratory at the MIT Department of Aeronautics and Astronautics, he was the lead scientist of the SPHERES program from 2005 to 2019. His tasks included development of research activities for tests aboard the International Space Station and in-ground facilities, including the MIT Space Systems Laboratory and the Marshall Space Flight Center flat floor. Alvar, we'll go to you now to lead this panel. You're muted, Alvar.
Of course I was. Thank you, Christy. I did not want to make any noises while you were speaking, so there we go. Really appreciate the introduction. Actually, that was a long introduction. I don't have as much introduction on our panelists per se, because what we do have is for them to show us a little bit of their work. But when Christy asked me to lead this panel, it was really exciting that I immediately thought of people that said, oh, I know people who are doing a lot of interesting things with lots of data in space. And that's where the panelists came from. And then, of course, we also want to reach out to our friends near UW, now that I am on this side of the coast. And that's where our other panelist comes in through here, too. So just as a quick introduction of the panelists and why I thought this was a really interesting group to have this conversation with. Professor Karika Hoy from MIT. She has a lot of experience working with CubeSats. Actually, I just had the opportunity to say congratulations on TROPICS launching, because even though in the standard NASA way of doing things, all of the NASA will say that TROPICS is a NASA project. It all began as a capstone project at MIT with Carrie leading it, called Micromass. And it was really exciting to see that. So she comes in with just years of experience, including industry and then academia, flying CubeSats. And part of her research is laser communications. In other words, getting lots of data from space. So hopefully we'll hear more about that in a minute. One of my last projects at MIT was with Frank Lind from the Haystack Observatory, which is a really easy thing. It's a little CubeSat that will have 6 channels of signal of SDR, software-defined radios. And that was a little bit sarcastic for those of you that don't know it. Having 6 channels of SDR on a single CubeSat is definitely a big challenge. And for this panel, it means having gigabytes of data and not being able to get gigabytes of data. So I thought, maybe Frank can tell us a little bit about how that can be managed when you don't yet have laser communications. Alessandra Babusia from JPL was one of the, let's say, my first graduate students when I was doing research at MIT. And she is an expert in communications, working on all aspects of that for JPL. She's been now at JPL for, is it about 10 years, I believe, Alessandra, who just joined us, and she's going to be on audio with us today. And Kevin Lally, who is part of the local space scene in Seattle, and it's a group that we are really wanting to reach out for. I hope to meet Kevin in person. I haven't met him in person yet, but I'm actually really excited to hear everything that they are doing, how they're working with other local companies. You mentioned earlier that you're already working with some universities across the country, so we wanted to work with universities not across the country, but right around the corner. But it just shows how we have people from all corners of the country right now working on the same thing. So with that, I was not going to show much of my research because what I wanted for them is to show their things and then to have an actual open discussion. And I'm hoping, I think a couple of you will have different points of view on some of the questions. And that's what we want to hear today from my perspective. What are different ideas on how to solve the different challenges that are coming up? I know Alessandra has a really short time, so if everybody doesn't mind, maybe we'll start with Alessandra. I will show her slides myself. And
Can you hear me?
Hi, Alessandra. Yes, we can hear you.
Finally. I've been fighting with the Zoom app for the last 10 minutes, but I'm glad I made it.
Yes, thank you so much for being here. And what we'll do is I'm gonna share your slides.
Yeah.
And then
I apologize, I'm on the phone.
No problem. Yeah. And then you'll talk over them. Are you able to see what we're seeing, or should I let you know where we're at?
I'm seeing you at the moment.
Okay.
But, are you sharing? Maybe you're not sharing
I'm about to start sharing right now. Yes.
All right. So I'll let you know what I see.
Share this guy. And then here we go.
Yep, yep, there it is. So yeah,
okay.
I thought, we talk about big data, and I do, as part of this work I do at JPL, I do small mission and big mission too. But I figure that for small mission is a little more challenging, the big data. For big mission, most of the time you end up powering them with big amplifier or big antennas, and you're sort of good to go. And you're very limited mostly by other factors like, your instruments or power constraints and other things. But with the CubeSat, I think it's interesting. So one of the things I've done a lot, I've done both LEO and interplanetary, and I think those are very different. And in the LEO that I put there is that they are generally short-term missions. They don't have navigations requirements. And the good thing is that you really get a lot of products that are available on the market for those. And sometimes you can even get, high data rates. But one of the things that we have found, and this is working on missions that have recently operated, is that actually sometimes you get limitation from other subsystems. So we had cases in which the radio was actually capable of doing more, but the bus and the links between your avionic was limiting what you could actually send to the radio. So that's interesting. Sometimes you get this limitation. And the other one that I think a lot of you have probably encountered is the NTIA, that at the lower frequencies, you get a limit on how much bandwidth you can occupy. So that's one of the problems when you deal with big data and small satellites. And if you go to interplanetary, so if you go to the next one, you have a different situation there in which, you have more navigation needs. So that sometimes restricts the type of radio you can use, because not all of them do that. And you have a lot of path lengths to cover. So while big mission, as I said, use big amplifiers, then there you are at a little more of a challenging situation. And then you got radiation hardening, all sorts of things like that. And you have also the fact that the real estate is pretty tight. So everybody needs to have a space. You got propulsion, you get more things that generally LEO CubeSat. And in that, you can't, quite pack sometimes the amplifier that you would like or the antenna that you would like. So you do what you can. And one of the things sometimes we do is a combination of, highly directed antennas, but also long comm windows. So you go slow and steady for a long time, and you get your data back a bit slower. So that's That's one of the things we've tried to do. And so if we can go to the next, with one of the things that we also looked at, especially at JPL, is how do we handle those amount of data on the ground? And one of the things that happens is that for LEO, you have a lot of choices because you have more, you know, you have NASA station, but you have more commercial and even university stations. And that really helps you because you can almost have dedicated things. It's not uncommon that some university have their own system, basically. When you go interplanetary, that's much harder. So you do have DSN, you do have ESA. One of the things we've tried is to upgrade universities' dishes to work for the DSN, which we've done with the MORAD dish. So we can go to the next one. I think. There you go. And oh, I thought I had the MORAD dish, but anyway, I'm just gonna say the MORAD dish is a 21 meter that we have refurbished. But another thing that we do is we try to fit many spacecraft into the same bin. So what we do is we do what we call multiple spacecraft per antenna. And this is not always useful because if you have spacecraft or CubeSat that are very far from each other spatially, you can't really point a beam to all of them. But in cases like, for example, when we deployed the EM1 CubeSat from Artemis right off the bat, you have this situation where you have multiple vehicles all around the same area. So what you can do is you can sort of like have a wideband recorder that records the signal from all of them. And that's what the 4MSPA, the opportunistic is actually. And then you can play it back later. Or you can have it, you know, live, which is what the MSPA actually does. And one of the things are coming new is the MUPA that is actually not implemented, but getting there. That is the multiple uplinks. So right now, this works only in downlink, which is still important because downlink is generally our more constrained link. But soon enough, we will be able to uplink from the same DSN station to multiple assets in a sort of code division system so that we can reach them and give them, you know, all our commands all at the same time. So that's one thing that we have been trying to do when dealing with multiple data, multiple spacecraft, multiple access, a lot of data coming at the same time from all these vehicles. And I think we have another chart. Probably, and that's the one I thought I had before. Here it is. And this is the use of non-DSN stations. So the MORAD 21 meter dish is a very interesting antenna that it's on MORAD State University, 21 meter. They had it there for since before 2006 when we were made more aware of its existence. And it was already working to track CubeSats, but at the lower bands. What we've done since then is that we've worked with MORAD State to upgrade it to X band mainly. And now we probably gonna add another dish for Ka band there. And it has supported a lot of these CubeSat missions, and that has been good because that was a dish that normally big mission wouldn't necessarily select. You know, if you are Mars 2020, you wouldn't want to use the 21 meter. But for the CubeSat was very good, especially for the lunar ones. And they had almost a dedicated dish that they could share across these 3 or 4 missions, and that allowed to, you know, download a good amount of data. So that's one of the things we have been doing, and we are going to do with other universities as well. So this is all what I had for my charts.
Thank you, Alessandra. Really appreciate it. And I would like to see if we have time to introduce the other panelists to introduce themselves first, but then I definitely would have some questions for you if you still have a chance when we finish the other presentations.
All right. Okay.
Thank you. Yeah, but we didn't have a very specific order yet, so who wants to go next? Anybody? Or Carrie, perfect. Thank you.
All right. First, I also wanted to say hi to Alessandra while I had the chance. It's wonderful to see you. And thank
Hi,
you all
hi.
so much for the opportunity. It's great to see so many familiar faces. So I'm Carrie Cahoy, and it's good to see everyone. I had the great privilege of getting to work with Alvar when I first arrived at MIT. He definitely showed me all the ropes and really was super helpful with getting my lab started and helping with the students. So thanks again, Alvar, for all of the leg up there. Appreciate it. We couldn't have done anything without you. On that note, I was going to share a few slides. I'm going to talk a little bit about, instead of using radio waves to get data from space to and from Earth, I'm going to talk a little bit about using lasers to do that. We have some work ongoing in my lab at MIT on using CubeSat laser systems. So if it's okay with Alvar, is now a good time to share screen? Okay, so I'll go ahead and try to do that. And I'll pull up, let me know if this goes into, goes into full screen appropriately. Does that look okay?
You're good. Yes.
All right, thank you. So, so I was going to talk a little bit about, in addition to the weather sensors that I've worked on, I was mostly going to talk about the LaserCom for this, kind of getting data from space to ground and ground to space type of discussion. So as we've been trying to move more data around, it gets pretty challenging to use radio. For those of you who aren't familiar, some of you, including Frank, who probably is going to wince here, are painfully familiar with how difficult it can be to license the ability to send large data volumes up and down to orbit and back down to the Earth. There isn't a lot of radio frequency spectrum, like number of channels that you can use for space data transfer. And these days, images and video from space are very large, and there's more and more of it. So getting it to come through on these already limited license availability channels is difficult. So we've been looking at using lasers to do this because a optical system like optical fibers can use so much more bandwidth in its channels. The frequencies are so much higher that you can get a lot more data. And even better, the spectrum right now is not really regulated. So it's a little bit like the Wild West. We've been looking at using these optical comm terminals to get data down from space to Earth. So the mission I'm going to talk about is just on the title slide here, is called CLIC, CubeSat LaserCom Infrared Crosslink. And it's a NASA-sponsored mission that we've been working with the University of Florida on to put laser terminals in space. So there are two phases to the CLIC mission. One of them is done on this CLIC A first part on the right. I guess it's on the left. So the CLIC A is done, and that was a 3U CubeSat. So a CubeSat is a loaf of bread sized satellite, and it has essentially, for all intents and purposes, a slightly higher tech equivalent of a laser pointer. It has a 200 milliwatt laser in the infrared, so your eye can't see it. It's redder than what your eye can see. So it's kind of invisible, but it's still a light beam that is coming down to a telescope on the ground from low Earth orbit. And our goal was to show that we could build a system that could make that link used with two big simplifications. One, we wanted to make it really, really small, and we wanted to use a low power laser so that, well, if you're in space and you don't have any air blowing by you and you try to use a high power laser, if you try to use a high power laser, you kind of cook yourself. You get really, really hot. There's nothing to cool you down. So you have to have big panels or some way to cool down. So we wanted to avoid using high power lasers. So we wanted to make it small and avoid using high power lasers. So we use a little MEMS steering mirror to steer the beam around on there. And then on the ground, we didn't want everyone to have a giant, astronomy telescope, radome kind of situation where you have cement pillars and giant telescopes and cryogenically cooled detectors on the ground to be able to get your data down. So we wanted to be able to do this with a telescope that you could buy off of Amazon, and then like an amateur astronomy class telescope, and maybe have a couple extra special cameras on it, but otherwise something that you could put in the trunk of your car or throw in a shed and put up anywhere on the Earth and still be able to get data down from space to it. Mostly to get around those pesky clouds, because light doesn't go through clouds all so well. So the more ground stations you have, the more diversity you have, and the greater chance you have of being able to do a downlink. So that's this first part of the mission. The Click A part was just the CubeSat to the terminal on the ground. The BC part is doing the same thing, only this time with a crosslink and being able to measure the ranging between the satellites to the sub-centimeter level. So to have a special timing chip on board that lets us do precision ranging so we can transfer lots of data and know where the other guy is really precisely. So that's the one that's coming up. So I'm going to talk a little bit more really quickly about this Click A one since we just finished it. If you look at the date, it just deorbited last month, end of March 2023, and I wanted to show a couple pictures and then I'll hand it back over. So the main idea was it launched in September of 2022, and if we were doing this again, we didn't really have much control over the launch, but it ended up deploying us right before winter. Winter in New England is not the best time to be outside doing LaserCom downlink experiments. So next time, we should really do the demo in the summer. The students will be warmer. But the idea was to deploy it and then to have it contact the ground station, which is in Westford, Massachusetts, right down the road from where Frank Lind, who's on today, works. And so the idea was the ground station at Westford would send up a 5-watt laser just to have the satellite be able to identify where the ground station was. And then this tiny satellite, the CubeSat, would transmit its beam down to the telescope, and that would pretty much conclude the experiment. So this is a quick picture of what the transmitter looks like that's on the CubeSat. It's all commercial stuff that you can buy for the most part. I mean, you'd have to manufacture the housing and the mounts for the cameras yourself. But other than that, most of the components are things that you can buy and put together. So we have this a calibration laser in the system, and then the redder than red 1550 ITU C-band downlink laser. And then we have the ground station, the amateur astronomy telescope uplink beacon laser that's also redder than the eye can see. And that's kind of what it looks like. It fits in kind of a coffee mug sized container. This is the shed where, and I warned you about the deployment in September. So there's snow on the ground, but there wasn't a shed before, but it turns out building a shed to keep your telescope stuff in dry and clean in New England is not too expensive. It's actually pretty reasonable. And I know during COVID, a lot of people built sheds outside anyway to have like private space when we couldn't go anywhere. But yeah, so the roof on this particular shed, it looks like it has a porch, but that's just where the roof slides over to open up. So it can make the contact. And this is the telescope. It's a Celestron 1100, which you can buy on Amazon for a couple $1,000s. It's not super expensive, with some of the, add-on detectors that we use to help it be able to track the satellite and stay controlled as it tracks the satellite across the sky and looks for the beam from the satellite. So these are just the little closer up pieces of, we made a 3D printed bracket, and then we upgraded to aluminum to hold the equipment on the backside of the telescope where you normally put the eyepiece. And then we have a little bit of a collimator on the front of it so that we can send the beacon up to the satellite. But other than that, it's pretty much fine. And then these are two of the graduate students, Will and Peter, who are working on it up, and Jacob was up there too. And this is a video of the beam from the satellite coming down to the ground station. And so it's kind of fun to see that, these things work, and they're a good way to get data from space down to the ground. So that's pretty much all I wanted to open with, like something fun and new to look at. That's kind of a hot off the press result that was kind of fun to see, and to note that when you get deployed from the space station, you don't get up stay up in space very long. So this is the September, and this is our deorbit. So this is basically around March when things started to get difficult to start controlling on the satellite because of the drag. But yeah, so I'll stop there, and I'm looking forward to chatting more with everyone on the line.
I guess I can jump in next if that's okay.
Berg, thank you, Kevin. Go ahead.
Thank you. I just heard so much overlap already. I don't know if I can handle any more kind of dots to connect. And I made some hot edits here, so slides are coming up. Does that look okay?
You're good. Yes.
Okay. So yeah, thanks everyone for having me, and those in attendance for listening in. My background is originally in optical systems development. I went to Montana State University for both a physics undergrad as well as a master's in science and engineering management. And Montana State is definitely a bit of an optics hub, kind of going back to even the 50s and 60s. Did a lot of early work around laser crystal growth, gain medium development, and really, since then has made all kinds of strides. From everything from LiDAR measurements, including atmospheric, like differential LiDAR, to the technology companies that have spun out around that. So it was a really cool place to get start getting steeped in that domain knowledge, and also get some exposure to successful academic to commercial spinouts. And where that took me, after I finished my master's, I came out to the Seattle area to build this 6U CubeSat system here, and my contribution to it was primarily the infrared imager that you see up here in the top left. On the right is kind of a high-level overview from the time I came in to the time we launched the satellite. So it was a 2-year timeline for that portion of the effort. Certainly before I showed up on that 2016 date, much work had been done. Planetary Resources had already launched a couple of 3U CubeSats, which contained most of the avionics stack that was reused here. And similarly for this 6U implementation, some groundwork had already been laid, but regardless, it was a very quick turnaround project for a very unique commercial capability at the time. So this was over 5 years ago now that we launched. We operated this satellite. We made contacts with a ground station in Redmond, as well as leased stations such as in Alaska. So it was a pretty great achievement to get some data back from this sensor. We had enough time to do some comparisons between what we saw on orbit and the calibration that we'd performed in the lab. And so that is the lower left image here. Maybe a bit hard to see what's going on there, but essentially we just lined this instrument in front of a temperature reference standard, and that gave kind of a basic calibration for this this broadband midwave infrared imager. And I'll just add a little more while I'm on this slide. Essentially going through this whole process again with a new company called HydroSat. Well, more recent. So HydroSat has existed for about 5-6 years now. I joined 2 years ago, and we're continuing down actually a similar path of providing low-cost thermal Earth observation systems. There are a lot of downstream applications once that data becomes available on What we really need is a daily cadence, and what we currently have is about 10 times less frequent. So we are driving improvements in the cost efficiency of these systems without sacrificing the scientific data quality that, you know, we're essentially at Hydrosat trying to hit a bar similar to like Landsat tiers. So we're really trying to provide data that is what application scientists have come to expect working with flagship missions like that. To do that, our instrument for Hydrosat, just the thermal payload that we're bringing to the table, it's twice the size of the entire satellite that you're looking at. It's a much bigger telescope, has thermal control included throughout. So it is a much more complex system and higher swap footprint, we would call it, to achieve that capability. But things have progressed so much in the last few years that we are able to do that in a fairly lean and cost-effective manner, and we're looking forward to having 2 satellites up next year. This is really quickly a slide I wanted to show because it was the intended next evolution of that system we were developing at Planetary. So you'll see, you know, even back then we were thinking better had to mean bigger. So this is a 12U form factor design, and we are really taking up all of it with the optics. I'll say this is a good example of bad ideas that can kind of come into the fold when you're really squeezing things. Hydrosat is not flying on CubeSat. We'll be more in the microsat, kind of 150 kilogram satellite mass. So again, just the capabilities that are available in the kind of new space commercial side of things are just constantly improving, and we're trying to leverage the best of what's currently out there. So going back to, you know, Carrie's laser comm work and leveraging as much COTS as possible, that was very much our intent back working on this system, and still remains true. But sometimes when you're really trying to push on capabilities, you can't necessarily use those off-the-shelf components. I spent a couple of years at Amazon Kuiper and set up some optical testing capability for them. Kuiper, I'm comfortable saying, has certainly considered laser intersatellite links, such as SpaceX has enabled in the last year or so. There are some pretty fundamental reasons why that's a huge competitive advantage for these high data rate mega constellations. I won't say anything about, you know, what current plans are for Kuiper, but the intent of this setup was basically to show some folks higher up in the organization, you know, what these systems could do, and also how complex they were. So it was a sprint over about 9 months to pull together 2 prototype terminals and a bunch of test infrastructure to send data from one terminal to the other, and that was presented internally at Kuiper to help guide future decisions on the architecture of that constellation. And just one more project here I'll flash quickly. Another Planetary Resources era prototype. We split our attention for some time between thermal and hyperspectral. We eventually decided to focus on the thermal, again, 5 years ago, and one of the biggest drivers in that decision was data downlink limitations to ground. So it's something that comes up pretty quickly when you're running the numbers on high band count, high resolution satellite imagers. You know, if you're intending to run those all of the time, the data just explodes quickly. So again, nowadays, we have bigger pipes to the ground. We have potentially more inter-satellite links coming up. And this type of system is, I think, fair to say, much more practical to implement these days. And we see some other commercial companies kind of picking up threads like this, as well as interesting systems coming out of places like Lincoln Labs and other flight centers around the country. So I will end it there, and thank you very much.
Kevin, thank you. Really appreciate it too. And Frank, do you want to conclude our introductions of what are you guys doing?
Sure. I'm going to, can you see the slides, Alvar?
Yes, we are good.
All right. So I'd like to, thank you for the opportunity to speak to everyone today. It's a lot of fun. I get to see Carrie when we're on Zoom together rather than actually coming down to campus to visit. We should probably fix that at some point. So I'm going to tell you a little bit about what we do at Haystack Observatory. I'm going to go through some of the data aspects and the mission that Alvar mentioned, AeroVista, that I'm one of the PIs for that for NASA Heliophysics. Carrie, of course, is on that mission with me and her students, and have been a great contributor to it. And Alvar worked with us for a few years on software. I'll also talk a little bit about the spectrum innovation work I've been doing under an NSF center called SpectrumX that has a little bit of relevance to communications with space. And Haystack Observatory, for those who don't know, is about 45 kilometers away from MIT campus to the northwest up in Westford, Massachusetts. We have a variety of radio science and space sensors. Most of the systems you see in the photo are between 37 and 68 meters across in aperture, and they're almost all active systems, whether it's radars or I actually have a SATCOM system I'll mention at the end. But we do a lot of radio science, we do a lot of space science, we develop instrumentation, and then we work with MIT Lincoln Laboratory to provide space debris and surveillance activities for the US government. The AeroVista mission that was mentioned has been a consuming factor for a few years for us. We're actually kind of in a pause at the moment because NASA Heliophysics budgets have been a little tight. And so we're on hold for the moment until funding improves, I guess, or we get another sponsor to get to orbit. But we have two satellites we've been developing. They're 6U CubeSats. One's named Aero and one's named Vista. There's some acronyms that go with that don't really matter right now. And they're going to end up in polar sun-synchronous orbits between about 400 and 600 kilometers. And they're going to be doing radio measurements there using a very special sensor called an electromagnetic vector sensor that lets us get direction of arrival. And in particular, we're interested in auroral radio emissions and the ability to image them and do interferometry. And these satellites are going to just be, passively controlled. They don't have thrusters on them. We're going to use drag control for relative positioning. The big picture goal behind AeroVista is to enable future low-frequency radio astronomy constellations in space. So, this is the get one up there, get two up there, and then eventually you can get 10,000 up there maybe and do some really interesting exoplanet research and radio astronomy research. But, this has been a big mission for us. Underneath it, there's a lot of really interesting science you can do with one or two platforms in space that can measure at low frequencies. The frequency ranges we're working with, which are between about 100 kilohertz and 15 megahertz, don't get to the ground by themselves. The Earth's ionosphere will reflect them back into space. Now, it turns out some energy makes it to the ground, and how that happens isn't really well understood. But we're going to, fly under one of the major forms of radiation that the Earth produces naturally, called auroral kilometric radio emission. And we're going to be able to measure this with kind of a direction finding and imaging capability. And then with the two satellites, be able to do interferometry. And the interferometry is very challenging because we actually have to bring raw data to the ground off the satellite ADD converters. So it's filtered, but it is very voluminous. And so this gets into a science mission that is very ambitious, where the levels and the amounts of data really push what you can do with radio. We very much love Lasercom for future satellites. We definitely want to just stream all the data to the ground. Now, the sensor that we've got is a very interesting sensor called an electromagnetic vector sensor, and there's lots of literature you can go look up on these. Essentially, it's a kind of array antenna, and in this case, it's an array antenna we're going to deploy from a CubeSat. So there we have a mechanically deployable antenna for space, which is going to be about 4 meters across in each direction and 2.5 meters high. So there, that all by itself is a challenging problem. It has 3 dipoles and 3 loops, and they're all orthogonally oriented, and they have a common phase center. And this actually allows us, if we sample them simultaneously, to measure the full electric and magnetic field vectors. And that gives you a Poynting vector if you take the cross product. So at first order, you can think of it as by using the electromagnetic waves motion across the pattern of the antenna, the patterns formed by these antennas, we can actually determine source intensity, direction, and polarization. And some of that comes into some statistical methods that really make it a much more capable sensor than you would immediately imagine. The other thing you can do with this that's very interesting is you can form nulls in various directions. And that can be very useful for potentially doing low frequency radio astronomy close to Earth. Because one of the big challenges is space is not radio quiet above the ionosphere, is all these satellites are up there that everyone keeps building, and they put out a lot of electromagnetic emissions, some of them intentional, some of them unintentional, and it forms a level of interference that's probably problematic for a lot of astronomical things we might want to do. Just to give you an idea what these satellites look like, these are the actual flight model units that are in Lithuania at the moment being tested. We're like 6 tests or 7 tests from them releasing these to us for delivery. We got Aero on the left and Vista on the right in that lower left image, and then these 6U CubeSats unfold to get us enough power to run the satellite. We've crammed them about as full as you can cram a CubeSat. There's probably somebody who's managed to make something more dense, but I'd be hard put to actually do that. We have, importantly, kind of all the normal bus things. We have 3 radios in here. We have an X-band radio for high-speed downlink, and in particular for basically data dumps down from orbit. We have 2 UHF radios for redundancy, and then the X-band radio is a little faster uplink capability than the UHF. And this level of redundancy we built in because we've seen a lot of CubeSat missions that have radio problems. And then the X-band capability is, of course, so that we can really get the data off the mission. You'll see in the kind of middle right on there a thing called the Aurora radio. I'll talk about that next. That's the data generator there. It hooks up to this deployable vector sensor antenna that pops up like a little jack-in-the-box and unspools. And don't ever underestimate how hard it is to make deployables, is all I have to say. It's a lot harder than anyone would ever expect to make a jack-in-the-box work in space. We also have a couple things there, ASP A and B, which were the student payloads, which are just awesome little camera magnetometer combinations. Those have really, I think they're actually almost through environments, and they're really, really working well. So we're really happy with those. And then one of the other things, that this thing has is we have some pointing requirements, but they're not really tremendously good. But there's a star tracker on there and the normal sun sensors and GPS. So the software radio developed is really, I want to do real science in space. Looking at the Earth's radio aurora, people haven't done any dedicated missions for it that I'm aware of. There's been a lot of incidental things over the last 60, 70 years. But to do this, you have to actually collect data. And, with a frequency range of, 15 megahertz, sampling everything with high enough dynamic range for the mission, is challenging even with a couple channels. We had to, with the vector sensor, have 6 channels. So we actually have 6 channels at 16 bits and 50 megasamples a second. And for a ground-based instrument, that's nothing these days. We are often building instruments that are actually processing and collecting, say, the latest EHT stuff is doing 256 gigabits a second of high-speed sustained recording. But for doing this on a CubeSat, it's very, very challenging. You don't have infinite power. You don't have infinite space. So one of the things, there's acquisition, and you have to fit it within your power envelope, and that's very challenging. One of the next things you've got is you actually do some real-time processing on this. We do this within FPGA, and one of the things we're doing that's a persistent pattern in data from space is we create some summary information. We do an FFT and integrate in real time that gets us summary plots. And then we do a coarse polyphase filter bank that actually is the data collection portion for the science data for the mission. And this is a filtering method that lets us select a subset of the input data to record. And so we can really throttle it down to about 781 kilohertz channels if we want, and just record, say 6 of them, or we can open it up to whatever we can sustain to the SSD storage on board. So that's all done in programmable logic. It's highly synchronized to a chip scale atomic clock. And we timestamp everything very, very accurately so we can do interferometry between the satellites and align the data. This all gets transferred in real time to solid state storage as a data acquisition swath occurs. We then have a post-processing interval, which could happen later, that we call in-flight processing. And this is a combination of CPU and FPGA accelerated processing, where we can go in and filter the data to make it even smaller, right? So we can pick a bandwidth and take an even narrower bandwidth. We can also do what's called covariance processing, where we cross multiply all the elements and then basically do some averaging on the data in order to get the fundamental vector sensor direction of arrival information in a form that is, really general for the signal processing, but which is much more compact for being downlinked. So the primary data products off this mission we actually bring down are the FFTs first. We use that to select intervals to process with ground in the loop. And then we uplink, process this chunk of stored data down to covariances. And we'll bring a lot of covariances down and a very small amount of fine PFB data for interferometry. So this is very much a filter when you look at it from the data transfer and management point of view. Is we have a very high speed data acquisition at the edge. Then we have real-time filtering and processing. And we managed to get this whole thing operationally into about 15 to 17 watts. It'll be under 20 watts at full temperature range for the instrument. Now, once you get all that data, you have to be trying to, collect command control and bring that data to the ground. And we made a choice in this mission early on to leverage 2 high aperture antennas. One of them is the Moorhead State 21 meter, which was mentioned earlier. The other is the Westford 18 meter that we have at Haystack that we've upgraded to be able to do some SATCOM applications. And underneath this, there's a ground station interface. So there's something talking to that telescope and the radios to make them do the demodulation and the packetization and to get data down. And then the data that we're actually going in and out of the bus is something called CubeSat Space Protocol. It sounds better than it is. It's a data format, right? With some messages, some ability to do some routing with it. And the data comes down, into a mission operations infrastructure that we're actually virtualizing. And it looks like the software services chain for modern software processing. So these kinds of stacks exist in all kinds of event-driven real-time systems that run our modern lives on the internet. And you just don't see it. It's running on Amazon and hidden behind the scenes. But we have a pub/sub broker system that takes in or generates these messages. So these are like channels, and you say, oh, I want to hear everything coming off of Arrow, and I want to hear the packets that came from the X-band radio. These packets then ultimately go into something that translates them, validates them, and turns them into actionable data of some kind. Sometimes that might be a file transfer off the platform. So a lot of our data is going to be file downloads that get put in a file system, just like on your computer. And those file system transferred data, are really focused on the science mission data. We also have much smaller events, which are real-time telemetry that come off. And that real-time telemetry goes into a recorder that, actually ultimately goes into the cloud file system or into the time series database, which then lets us kind of have visualization and user interfaces off that. Now, the science data that comes down goes into a mission workflow system where basically data shows up and it triggers certain automatic processing, like the generation of summary plots. And that's what the ground operators use in the user interfaces to try to understand what they want to process and what they want to downlink. And on the right hand side, there's some mission control tools to actually send commands and do some scripting. This stuff is, some of this we're getting from the vendor ultimately, some of this we have to write ourselves. And we're leveraging some things like OpenMCT from JPL that are available and really very nice and usable. So that's kind of the flow that, the scientist lives at the output of these mission workflows, and you can have another database there to let them do stuff, and you can have machine intelligence down the road that does all this. But at the end of the day, we're taking something that really is high-speed acquisition at one end, and we're applying rationally chosen filters in order to downlink data. Now, there is a step beyond that, which would be to make intelligent filters at the edge of all this, right? That's a much harder thing to validate and to create, but it would potentially make the mission much more flexible in, say, catching events that weren't where we expected them, right? We kind of expect to see radio aurora when we're near the Earth's auroral zones, but there may be other things we could pick up that would be really interesting that we would not detect if, with our normal data acquisition. And in the future, you could imagine much more intelligent acquisition that really acts to filter what the humans on the ground have to see and deal with in order to make it possible to operate, much more sophisticated or much larger constellations of systems. And we've architected this around 2 satellites right now, but the idea is to have something that can scale ultimately into more satellites. And there's a lot of work on this one. I put an under construction under here for a reason, but I'll mention we've done some SATCOM development for NASA, and as part of this program, we actually have a very sophisticated UHF feed that's a phased array feed on our 18-meter telescope that can both transmit and receive at UHF for SATCOM. We also simultaneously have an X-band, well, it's actually a 2 gigahertz through 14 gigahertz downlink capability with a cryogenic feed at the center of this. There's a thesis on this if you want to know too much detail. On the lower left is us looking for an MIT satellite. We're actually searching for signals from MIT BeaverCube in this, and there's actually half a dozen CubeSats in this. It's a really amazing scan, and BeaverCube was not in it, which was unfortunate. I was sad, but yeah, I know, Carrie. But nevertheless, we've stood this up. It's an interesting system. We've learned that our operations team and radio astronomers really don't like doing SATCOM. But we kind of twist their arms and make them do it. There's certainly, for things like higher power levels or other frequencies, we'd have coexistence challenges with our radar systems. Now, one last thing before I'm done, I'll give an aside on spectrum coexistence. I'm also part of SpectrumX, which is an NSF-funded center to look at the radio spectrum and the future of it and how we can dynamically share it and how we can handle coexistence issues with what they call the passive services like astronomy and other applications of the spectrum. And there is an unimaginable amount of discussion in this about the satellite constellations and the coexistence with coming 5G communications to and from space, which is on its way. And underneath it is all these satellite transmissions are RFI for things that would normally use the radio spectrum in or near the bands of the transmissions. And certainly radio astronomy has kind of staked out and occupied a huge amount of the millimeter wave spectrum, which people are eyeing and wanting to get back for communications applications to and from space and for crosslinks and things like that. And the power levels that can cause interference can be way, way, way below the emission mass requirement levels. You can get interference very, very easily. And the really scary thing is, if you go to this satellite map.space here, you can see all the SpaceX satellites for Starlink or, flying around. And at any given time, there's 10 of them at high elevation angle looking at Haystack or near to Haystack. And interference from this, can be problematic for the telescopes. And so really technologies that let us share and adapt how the radio spectrum is managed in time, frequency, and space for satellite constellations and their relationships, not just to ground Earth stations, but their relationships to other users of the radio spectrum, radiometers in space, for example, looking down, radio telescopes on the ground looking up, is really an open area of research. And there's a lot that can be done both technologically and in other things in terms of coordination, policy, standards. Maybe we can finally get a rational way of allocating frequencies for satellites, for example, where it's easy and where Earth stations can talk to whatever that they've got the crypto key for or something. There's lots of better ways to do this. So I'll end there and thank you. And we can have questions in a bit with, I guess, Alvar.
Great. Thank you, Frank. No, I think it's amazing. And I think it's really that last one that you left it for last, but you left a really important one for last, and sharing. And unfortunately, our JPL guest Sandra had to leave. She had other commitments too, and But I think it was what you said there was almost directly to what she was saying, right? You need to share, you need to do a lot of figuring out how to share the spectrum on Earth. And she was saying, well, we also need it for deep space too. And that's actually really interesting how the needs for deep space and Earth apply. But I know Professor Cahoy also needs to leave soon, but before we get a chance to not get questions from her, Amy, I say you come in. Do we have any questions already, and especially if they're for Professor Cahoy? And if not, I have a couple things I could ask myself.
We have one question right now, and it is, are there any downsides to laser-based communications as compared to radio communications, i.e. higher pointing accuracy requirements? What are the implications for missions which aim to down/uplink a large quantity of data using lasers?
Yeah, those are great questions. Yeah, I mean, the downsides are, as noted, clouds and pointing. The pointing, I think, is manageable with some of the technologies that we have for steering small mirror systems and for precisely controlling satellite terminals. And I'm working on some other cool optical technologies that I'm happy to chat about maybe offline to help control beams. So that's a challenge. I think at some point, though, my vision of where things are going to go with this are that there will be increasingly less need to get data down and up. I think a lot of the processing is going to be moving on board. The data that is taken from space will be moved around and combined in space, processed in space, and lower rate insights will be downlinked. This is kind of what I see on like the 10 to 20 year horizon. I don't see us needing giant volumes going up and down anymore. I see it as a sea of data going overhead, and then the insights that are needed to the devices and teams on the ground are communicated downward. So I see that happening eventually. So I think at that point, maybe we use radio to get through the clouds consistently, and then we use optical for timed larger data downlinks over better weather locations. So that's one thought. The other one is that having the portable terminals and a large number of them means that you can have a network that is robust to transient weather systems, which you can use your on-orbit data to predict and turn on and off with weather systems as they go over. So it's kind of this future vision you have of being able to observe systems and processes happening and then rapidly control your response networks to react to them. So it's a fun vision. It'll take a little bit to get there, but those are tough aspects of laser comm.
I think we already hit on the main technical challenges that that tend to come up. I had one more to potentially add and interested in thoughts on this, but I think the standards are for sure less mature in it, you know, at least in the context of using these links in space. So many different kind of modulation approaches have been invented to optimize in different cases, right? And Alessandro was mentioning that sometimes, well, generally we tend to think of laser links being like the really high volume, the really fast ones, right? And you know, maybe they're ISLs, maybe they're getting you a bit further to the moon and back. But also you have cases, and this is the reason that Planetary Resources went a bit down this path, that just having a trickle to something like very far out can be advantageous also. And so what I've seen is kind of many different, there's kind of like a jungle of different laser link architectures to support these different use cases. And I know that's probably true on the RF side as well, but I think there's probably a better mapping, like a better taxonomy for RF where the you know, the right solution is maybe a little bit closer in reach. And this is something that a lot of the various DoD programs are looking to accelerate on specifically the standard side of optical links. And I would hope that, you know, we all eventually see some benefit of that as well as these become more prevalent.
Thank you, Kevin. Yes, I think that's. I mean, we're seeing the different types of technologies, and they all are have their challenges. Again, respecting Carrie's time, I wanted to see, Carrie, do you want to have any final words? And we'll let you go, and then we'll get Frank and Kevin to discuss and have some fun conversations for a few more minutes.
And there's one more question for Carrie, if maybe we can try that. Does that work, Carrie?
Yep, that's great.
What do you see as the biggest barrier to achieving that vision of in-space data processing? New radiation hardened hardware, general infrastructure, or something else?
Time. I think it's people time and getting the momentum to make the investments in the hardware development and placement on orbit. So I think those are the hardest things. I think we're largely ready for it. There are ways to manage radiation effects on fast commercial processors on orbit that have been being tested and demonstrated. Radiation tolerant chips can be used as kind of a watchdog instead of as the main processor, and to help control these systems. So I think we're close. I think that a lot of the challenges too will be power management, and the biggest missing part, as far as I can tell, is a robust intersatellite networking environment with the ability to add and drop nodes like we do with Wi-Fi on the ground, and being able to do that in space. That is a big gap that we have not been able to fill right now. And a lot of the on-orbit communication networks are very point-to-point still. So I think getting to that point with hardware that can make that kind of Wi-Fi equivalent environment happen on orbit will be what lets this happen.
Carrie, thank you so much. I really appreciate it. Thank you for joining. Sorry to make you run to your next meeting.
Yeah, I'm so sorry that life is
but
on the hour, not on the 15 minutes.
Yes.
Apologies.
Really appreciate it. Thank you.
Okay.
Yeah. And but just continuing with some of the questions. I mean, I actually, of course, I had other questions, but just if we continue this thread to get a little bit more of Kevin and Frank's opinions. So Carrie just said, well, the idea is let's process the data up in space and send less data down, which is very interesting. And I think, well, I know Frank is Aerovista's doing that in many ways.
I mean, I alluded to that, Alvaro, with the idea of kind of machine learning at the edge being the satellite, and trying to be intelligent about bringing things down. I think we have another real challenge at the device level, though. We're kind of, and this is a much bigger challenge than just kind of space radiation tolerance. It's that we have a lot of device technologies that very often, you know, you really want them in a customized form. So like, say, take just like the NVMe SSDs that you have in your computer, right? We're using an automotive one for a pair of them for Aerovista, with the idea that they're kind of vulnerable and one of them's going to die, all right? And we have a switch to switch between them and kind of the minimal electronics in between. But, you know, at the end of the day, we're relying on, well, one's powered off and one's on, so only one of them is going to get zapped at any given moment. And that's kind of a weak assumption. And, you know, what we'd really like to do is have an NVMe array with a custom controller that had some redundancy in it, right? We'd like that to use what we know about building radiation tolerant circuits to do that. Now, the problem is there's no commercial market on enough scale to get a chip vendor to go and put the resources into that. And government, even when you look at it, very often doesn't want to put their money there. They've got other places they need to put, you know, too much money. So, you know, you end up in this gap where you need customized things at a moderate scale. You need tens of them, or maybe if you're doing a satellite constellation, thousands. But in order to get a chip vendor to go make the stuff, you need 1 million. You need to sell 1 million, and there's no guarantee there's a market, so they're not willing to do it. And that gap, that mid-scale manufacturing gap, shows up all over the place. It's on ground systems, military systems, anything where there's kind of customized environments or you'd really want to tailor for low power. And I think solving that, so that you could go out and make a tailored, SSD array that combined the inexpensive commercial, say, chiplets or components, along with semi-customized things that provided the radiation tolerance or the environmental performance things you needed, would be an absolute revolution in making this happen. And I'll tell you, my worry about Carrie's thoughts on this is that I can put up redundant processors. We're doing, AeroVista, we're using a commercial processor with a Watchdog that's more radiation tolerant. But at the end of the day, if I get a big enough event on the sun, all the satellites are going down that rely on that. And every single one of them will just die. And we are going to witness an event at some point. Maybe, might not be in my lifetime, might be 200 years, 300 years. We will see the sun do something at some point, and everything's going to go pop that isn't hardened enough. And you can imagine as we build more and more infrastructure, well, it's one thing if Elon Musk is willing to watch 20 satellites burn up because he launched them, and didn't get them up in orbit fast enough, right? And just shrugs and launches another 20, right? It's a whole nother thing if 34,000 satellites go down all at once, right? And so I think we have an immense challenge for aerospace engineering and for radiation tolerance and computing. And all the clever stuff, we've got all kinds of clever techniques and mathematical approaches and ways of building circuitry, but the problem is we can't implement them in a cost-effective manner at any kind of scale.
Okay, that's I don't have an answer either, and as you know, I do love avionics, and that actually has been FPGAs gave a little bit of hope at some point, in that you can create redundancy at the silicon level in some sense, at the transistor level in some sense. But then we also realized that the FPGA manufacturing process makes them way more susceptible to radiation issues. So even though we added radiation, it kind of evened out at the end of the day. I wanted to ask Kevin if he had any thought processes about that, or I wanted to introduce one quick concept, but maybe it's for both of you. So we'll just say for both of you. But it's in one of my questions, the way I put it, and one of Carrie's answers was, well, we can make all these small ground stations. So where does amateur people in the ground fit in this idea that there's all of this data coming down? I mean, if everybody buys a telescope with a laser receiver for fun as a hobby, Carrie's idea could be better, but should we be dependent on a lot of amateur work for some of this data from space? Should we crowdsource radio communications with space?
I don't know as much about the RF side of this, but I will say that crowdsourcing the optical measurements is an effort that kind of came out of the end days of planetary resources, but also is one I think that's bubbling up again in the new space world, right? I believe Privateer just announced some partnership to support this kind of concept for optical satellite tracking. And, it's something I'd love to run the numbers on myself. There are certainly a lot of constraints around when that type of measurement is going to be valuable and who's actually going to be able to maintain the hardware. I think certainly it's a fun idea. And if I had more free time in my weeks, certainly would consider throwing a tracking optical telescope on the roof and seeing if I can match up to some TLEs. But I see Frank's expression here that actually getting the volume of data you would need to improve the current state of the art. I think there's a pretty huge gap there, and I think some of these ideas around distribution of, many lower costs, but potentially simpler systems distributed, I think can be valid, but really need to, be assessed in the context of like, what is the total cost? And if you need all of these operators everywhere, are they just giving up their free time? Like what is the incentive there? I think, most projects to be seriously considered in this vein, like I would at least like to see some kind of incentive to get, it's more than amateurs at this point, right? You really need to have the background to bring value into the equation. And I think it's kind of tough to see anything playing out to fruition if there isn't that incentivization.
I think the incentive matters, although I'll say, so we've actually talked in SpectrumX a lot about incentive models for things, right? How do you get people to do X, Y, or Z in the radio spectrum when it's not really in their interests normally? You want to create incentives to make it in their interest, and then they all of a sudden participate and do so. So I'll throw this out there. I was laughing actually because I thought of this, which is, there's something for the Uber or Lyft of downlink, all right? So if you had a model where you had kind of a company selling access to this, and there were little terminals for $29.99, everybody could stick on their roofs. And, maybe you had a premium terminal for people at high altitude so you can solve Carrie's weather problem. And you're utilizing their home internet and 5G capacity. And, I could see that working as a model as long as there was a broker involved that could provide some statistical on average guarantee of how much traffic you'd really get through the network, and and also provide the commoditization of the components needed to build it. I don't know how to do it where people just throw stuff together. Our experience with that is that stuff just breaks, and then they get tired of it because it was a fun project until it broke. And so I really don't see that working great. Now, I will say that there's a protocol called LoRa, which is normally used in the US, it's at 915 megahertz, and internationally it's at like 868. And there is a whole little thing where you take like a Raspberry Pi plus a LoRa, chip, and you put it out with a little bigger antenna pointed up. And there is a downlink telemetry open source thing that is totally collaborative among people to put these, put the transmitters on the satellites and get little bursts of data. It's like kilobits a second kind of on average, but nevertheless, it works. It's out there. You can go find it and participate in it if you want to. And it was really, when I ran across it, I was like, oh, how cool. They actually got this so that they've got like people using it from orbit. So it's not like impossible. And crowdsourcing has always astounded me at how willing people are for a cause that they're interested in, like science, or, like they, oh, could you please help us observe this upcoming solar eclipse? People are like willing to do that because they want to participate in something interesting technologically or scientifically, or they want to feel they're part of a bigger enterprise and community contributing something good for humanity in their day job. Kind of, they don't like it, but they like to come home and work on stuff. So I'm always astounded by how well that works. And we've done some crowdsourced distributed data collection up in Alaska, for example, that I thought it was a joke when we came up with doing it, and we put it in the proposal and it worked great. We gave people cell phones. They would walk up and press the button and exfiltrate data from the middle of nowhere. This is Ice Road Truckers land up there. And we were getting real-time telemetry feeds off of this in the middle of winter. I couldn't believe it. And so, some of this stuff can work way better than you'd think. But I do think that if you really want this as a part of kind of societal infrastructure, you need this broker incentive model. You need the legal support, like in frequency regulation and licensing, so you can actually have uplinks easily. That's not going to be easy in the current framework, the way Spectrum is licensed. But I think there's, it's as I said, it's the Uber or Lyft of SATCOM. And probably, and NASA would love that. They'd love to get out of the SATCOM business.
Thank you, Frank. Thank you, Kevin. That's to me that's actually what I meant by discussion. We are reaching the time. I saw Amy and Christy coming back. I don't know if they want to take maybe one question or if we need to say goodbye. So Amy, I'll let you run this.
Yeah, one more question, please. We have a question from Professor David Sheen. Hi, David. He is an adjunct in our Aeronastro department from Civil and Environmental Engineering, and he asks, Is there potential to use interferometry from laser comms to provide more accurate sensor, pose, and constellation geometry for Earth observation applications?
I mean, I can talk a little bit about that because I had a mission proposal that didn't get funded that was an interferometric constellation using laser comm to position the satellites accurately. And the answer is metrology is absolutely fundamentally possible with bidirectional links. With only unidirectional links, you can do a little bit for angles, but the bidirectional links let you transfer time. And the moment you can transfer time between clocks, you can start to time the links on the paths, and you can get very accurate distances. And the real thing you're going to run into, I think, is that there's going to become a limit very quickly on how accurate you're allowed to be as this technology matures. Even though things are export controlled, et cetera, there's going to be concerns about being able to precisely navigate satellites to destinations that might be troublesome for people. So I think that may actually, you might end up with a policy limit rather than a technological limit. We're certainly looking at radio astronomy in space for imaging black holes with extremely high resolution, and that requires interferometric baselines in space with operating frequencies for the telescopes up into the 200 plus gigahertz range. And the metrology required for that is incredibly high, is incredibly precise. And yes, it comes down that you are actually specifying the orbits accurately enough for at least a little piece of time to know exactly where things are to the millimeter or submillimeter. So it can be done. It's extraordinarily expensive and hard right now. People can maybe make that less expensive. You also, underneath that problem, have a very important problem, which is having really, really good clocks that are stable and low power. And the chip scale atomic clock's pretty wonderful, and we can put it on satellites. The JPL deep space atomic clock is not a small satellite thing. It's 100 watts and quite a few kilograms. It's like 25 kilograms or something like that. But you need that incredibly accurate clock in the 1 watt, few hundred gram level, and then you can revolutionize timing. But so there's like more than one problem there that's tied together to solve the metrology problem for satellites. But I think it's definitely laser links are going to make that possible. Yeah.
Thanks, Frank. And Kevin, you were also unmuting, so maybe you had some comments on this, and we could finish with that if that's okay.
I was going to give the quick positive answer, and I think Frank hit a lot of details that I would not have been able to use so succinctly. So yeah, definitely appreciate that answer and don't have much to add.
Amy? Okay.
Yeah.
So back. Okay. Thank you. Well, thank you, everybody. We look forward to continuing conversations and communications on satellites. That's what Spark is about, and getting more space out of Washington and working with everybody. Christy, back to you.
Thank you. Thank you all for the great session and all of the conversation. I'm sorry, we do have to bring it to a close, but I want to thank all of our moderators and panelists and Stan Schull for our great informed conversation today. And if you are sad to leave the great conversation and wonder what might be next and how to continue the engagement, you can keep an eye on the Spark website. So Amy, I think that's spark@uw.edu. UW Spark? Remind me what it was.
Spark.uw.edu.
There we go. Sorry, I just auto.
And
do it.
UW is UW.
Yeah, sorry for. Yes. Okay. And then just as a note, so University of Washington and College of Engineering here in particular are investing in growing our capabilities in the space domain, particularly for satellites. So there'll be plenty of upcoming opportunities. Today, we've just focused on a few of the aspects of satellites, but there are many others, such as on-orbit servicing, which I would have loved to have thrown some questions in there around this panel, but we didn't get there. Democratization of resources, policies for respectful use of space, and of course, the launch side of things. But those will be for a different day. So thank you again, and we'll see you all again soon.
Thank you very much. Take care.
Thank you.
Thanks, Christy. Thanks, Amy. Thanks.